let's work on solving this trigonometric equation using some identities. So you may notice as we look at this that we do kind of have two different trig functions. We have cosine involved and we have sine squared technically. We would rather not have two different ones. So what I'm going to suggest first is we rewrite it, try to make them all either cosines or sines. In this case, I think it's going to be easiest if we want to switch everything from sines to cosines. So what I'm going to suggest is we first use the Pythagorean identity. All right, the Pythagorean identity just reworked where we had sine squared of theta plus cosine squared of theta equals 1. We can rearrange this a little bit. If we wanted to isolate the sine squared on one side, sine squared is going to be 1 minus cosine squared. So I'm going to replace our sine squared of theta with 1 minus cosine squared to kind of get us going in the right direction here. So we have 3 cosine of theta plus 3 on the left-hand side comes down, and then it's going to be 2, and then instead of sine squared of theta, remember we're replacing that with 1 minus cosine squared of theta. All right, from here, now at least we only have cosines involved. Next, I'm going to go ahead and distribute on the right-hand side, bring this 2 to the inside, so it gets multiplied by each one of those terms. So 3 cosine of theta plus 3 equals 2 minus 2 cosine squared of theta. All right, so we have a cosine that's squared. We have a cosine to the first power. We got some numbers involved here. What I'm going to do next is just move everything to one side, because typically on these, we want to think about zero product property. Maybe we can factor along the way. So I am going to kind of move these all at once for us. I'm going to add 2 cosine squared. That'll move it over to the left-hand side. And I'm going to subtract 2 from both sides as well. Okay, so that's going to leave us with 2 cosine squared of theta plus bringing down the 3 cosine of theta. And then combining our like terms on the left-hand side, we have 3 minus 2 leaves us with positive 1. And on the right-hand side, we've kind of planned this out that 2 minus 2 makes 0. Negative 2 cosine squared plus 2 cosine squared. That's all going to result in 0 on the right-hand side. All right, well, at this point, we have an equation of the quadratic type, meaning the first term, our cosine squared, is double the exponent of our middle term. So what I'm going to suggest on this is rewrite this into something maybe we're a little bit more comfortable with. So I'm going to replace each of our cosines with an x. So a quick let statement here is going to say wherever you see a cosine, we can replace it with an x. So notice at the beginning here, it was 2 times cosine squared. Well, now it's going to be 2 times x squared. Plus 3 times cosine is going to become 3 times x. With a plus 1 comes down equals 0. You don't have to necessarily replace each of your cosine of thetas with x's, but a lot of students find this easier because the next step is we're going to try to factor what's on the left-hand side. And factoring, we're just more comfortable seeing that with x's. All right, so for our purposes, what I'm going to suggest is using the AC method, because I notice our leading coefficient is a 2 out front there. Sometimes that's a little bit more difficult to factor when you have a 2 instead of a 1x squared out in front. So I'm going to first calculate a times c, which is just ax squared plus bx plus c. So 2 times 1 makes 2. Not a very difficult number to be looking at. All the ways to factor 2 are just 1 times 2 because it's prime. And then we want to double check, does that pair add together, because our constant has a plus in front of it, to make the middle coefficient. So our middle coefficient's 3. Sure enough, 1 plus 2 add together to make 3. So if you haven't seen the AC method before, bear with me on this. It's actually pretty easy, but if you haven't seen it, you got a different method to factor this, go for it. AC method says you bring down that first term, you bring down the last term, and we're going to rewrite that middle term. We're going to split it apart into 2 separate terms. All right. and we use the coefficients we just picked out as those factors over on the right-hand side. So we said 1 and 2 is going to work. We're going to use 1 and 2 as the coefficients for our x term, that middle term, right? We're strategically splitting apart a 3x as 1x and 2x. Now, we need to make sure that if we combine these back together, we get back to a positive 3x. So in this case, I think we have to go positive 1 plus 2 more would make positive 3x. But where we're at now, we have strategically rewritten this left-hand side, so we have 4 terms. So what we're going to do is use factor by grouping. So we're going to group the first 2 terms together, and we're going to group the last 2 terms together. And as we focus on those first 2 terms, say to yourself, do we have anything in common? Well, it looks like both of these have an x in common. So let's go ahead and remove that common factor of x and think to ourselves, x times what gives us 2x squared? Well, x times 2x makes the 2x squared. And if we continue redistributing, we'd say x times positive 1 makes that positive 1x. All right, and then for factor by grouping to work, we should end up with the exact same thing in the second set of parentheses as we turn our attention to those last 2 terms, but they have to have the same thing in that set of parentheses. So we just kind of say to ourselves, well, do we have anything in common between 2x plus 1, from the previous line? And really not much in common. Of course, everything has a 1 in common, so let's use a positive 1 as a common factor between those 2. Sure enough, if you think about redistributing that positive 1, we'll get the exact same 2 terms back. So to finish up our factoring, what's out in front, the x plus 1 goes in one set of parentheses, and then the 2x plus 1 that's in the parentheses, a common factor, goes in a second set of parentheses. Now to kind of finish these up, what you want to do is you want to set each factor equal to 0, treat them as separate equations, and work on solving them down. So the first one's pretty easy. We subtract 1, move it over. We're kind of got x on one side by itself. This other one's going to take a couple steps where we subtract 1 and then divide by 2. Still not that bad. Kind of feels like we're done, but we've got bad news. Remember our original equation? It had cosine of thetas involved. We didn't have any x's involved, and we kind of made up x as we went through this with this let statement up here at the top. So what we want to do is we want to get theta back involved in our problem. So we're going to go back and replace each of our x's with cosine of theta. All right, from that let statement, got to get cosine of theta back involved. So cosine of theta replaces this x, it's equal to -1. Then over here, cosine of theta is also going to replace that x, it's going to equal -1/2. So a little bit further to go. All right. At this point, at least we have cosine of theta on one side all by itself. So kind of 2 separate problems here. On the left-hand side, what I like to do is go back to our unit circle and think about 1's -1 and 0 on the unit circle. Just trying to freehand a nice circle to go along with this. We'll deal with it. All right, why I like using the unit circle is because I know that points on the unit circle correspond with cosine of theta, comma, sine of theta, right, as ordered pairs. So in our case, what we're looking for is some ordered pair that has x as being a -1, like -1 comma something here for our y value. Well, I know where that happens on our unit circle. It happens over here at that ordered pair -1, 0. Now all we have to do is figure out what angle corresponds with that. Well, luckily enough, that's a quadrantal angle. That's where theta has to equal pi. So one of our solutions here is going to be theta equals pi. Now, in the original question, we were asked for just the ones between 0 and 2 pi. Sorry, we're all the way up here at the very top. Looking up here, we have between 0 and 2 pi. So I'm not going to add 2 pi times k at the end here. I'm just going with that's one of our solutions. All right, going back down here, let's think about cosine of theta equals -1/2. All right, so we've got one solution here. Let's try to find additional solutions thinking cosine of theta equals 1/2. Well, 1/2 is one of these ratios that comes up pretty often, but off the top of my head, maybe we don't know it. All right, what I do know is if I think about a reference angle, I know that if I plugged in, let me think, it's going to be pi over 3 into cosine, it would produce a positive 1/2. So let's make that our reference angle. All right, we're close, but we're not quite there. All right, next, with that reference angle in mind, let's think to ourselves, which quadrant is cosine going to give you a negative overall result coming out? So for that, what I like to do is go back to this mnemonic device that goes, all students take calculus. All right, this just reminds us which quadrant each one of these trigonometric functions is going to be positive in. So in the first quadrant, all of them are positive, but we're looking for when is cosine going to be negative, right? So it's not that, right? Cosine of theta has to equal a negative 1/2. So not in the first quadrant. In the second quadrant, first letter here, S, corresponds with sine has to be positive. But that also tells us that cosine and tangent are negative. So one of our solutions is going to come in quadrant 2. All right, what about the third quadrant? Well, tangent is positive in the third quadrant, but sine and cosine are both negative. Hey, we're looking for when is cosine going to be negative, so let's look for quadrant 3 as well. And then finally, what about that fourth quadrant? Well, fourth quadrant, cosine is positive, but we don't want cosine to be positive, so we don't want that quadrant. All right. Lastly, we actually have to find the angles in quadrant 2 and quadrant 3 using this reference angle. So what we'll do is the quadrant 2 angle, we're going to always draw our reference angles into the x-axis. So that pi halfway around is going to come in very, very handy. So what we're going to do is use our reference angle here into the second quadrant from the x-axis. And our end goal here is to calculate the angle that wraps around into the second quadrant. So like the blue angle that's drawn in there. To do that, our angle is going to be, you start with pi because that's like halfway around. But then we have to back it up and we have to subtract away our reference angle, which works out to be subtracting pi over 3 in our case. Let's clean this up a little bit. We can say pi is the same thing as 3 pi over 3 to get a common denominator. Bring along that pi over 3, our reference angle. Combine our fractions together over that common denominator. And we get theta is going to be 2 pi over 3. Kind of similar into the third quadrant. What we'll do is we'll start with the x-axis, which is pi. Then we'll extend past that using the reference angle into the third quadrant. So again, we're trying to calculate this angle that wraps all the way around and lands into the third quadrant with that same terminal side. So it's going to be theta. It's going to equal, we're going to start with the x-axis, which is pi, but this time we're going to add our reference angle pi over 3 to it. Pretty similar as far as the work here. We're going to get a common denominator by rewriting pi as 3 over 3. And then add these together and we get 4 pi over 3. So we get this solution for theta and we get 4 pi over 3 in addition to theta has to equal pi from that first equation that we solved down on our first factoring over on the left-hand side. So a lot going on with this problem. We ended up with 3 solutions between 0 and 2 pi, like the first time around. If you were asked for all solutions, you just start with the ones that we have, and then you add the period of pi, 2 pi, multiplied by k, where k is an integer, to the end of each one of those, and you could represent all solutions, not just the ones between 0 and 2 pi. But we weren't asked for that, so I'm not going to add it in. Hope this helps out. Good luck as you're working through these, using your trig identities and solving equations, figuring out reference angles.